It was an open problem from antiquity. For 2,000 years, people played with the ruler and compass and worried about that. I'm not cheating completely. I know where one point is already, the center, so I don't have to draw that. Here's the other. There's a half, and maybe that's a half. Get it in the hole, and I'll draw this semicircle. So he showed, this is going to be a big formula, that the cosine of 2 pi over 17 was equal to minus 1/16 plus 1/16 times the square root of 17 plus 1/16 times the square root of 34 minus, inside the square root sign, 2 times the square root of 17. You're allowed to take iterated square roots in this, plus 1/8 times a big square root of 17 plus 3 times the square root of 17 minus the square root of 34 minus 2 times the square root of 17, and then minus another 2 times the square root of 34 plus 2 times the square root of 17. That's exactly what you need to know to show that this segment, the cosine of 2 pi over 17, can be constructed with ruler and compass. Once you've constructed that, you make a perpendicular line and you look where it hits the circle, and then you've got your 1/17 of a circle, and you just measure it out, and it goes around 17 times if you did it exactly right. So that's what Gauss knew would work, and what does work, at least in principle, if not with a real ruler and compass. So in the Greek times, people were very interested in regular polygons and in geometry, at the dawn of geometry, really. And they wanted to construct as many polygons as they could, but regular, all the sides all the same length, all the angles the same. They were very interested in constructions with ruler and compass alone. Here's a good compass. Ruler meant just a straight edge, no markings on it at all. This one has markings, but I'm going to use it anyway. I won't use the markings. Here's a nice circle drawn with a compass in the old style. So if I pick a point on the circle, I'm going to draw a hexagon in a way that everybody will know who's ever played around with ruler and compass. I'm keeping the compass length the same as it was for the original circle. Whoops, ran out of ink there. There we are. But the ink is so satisfying to me that I don't mind the splotches occasionally. All the circles pass very nicely through the center, showing that I haven't changed the width of the compass. And now I have 6 marked points on the circumference of the circle. And if I want to, I can put lines through them, and I'll get a beautiful regular hexagon. Make the lines a little longer, it's even nicer. Ruler and compass constructions are something else. There we are, a beautiful hexagon. And of course, if I just connected 3 of the points, like these 3, I would get a regular triangle. If I have any line, I can divide it in half with ruler and compass alone. In fact, that's worth doing just to show how it's done. I'm going to use it a lot later. So suppose I have a line, and suppose I have a couple of points that were already marked on it. And I want to construct the midpoint of that segment and a perpendicular line through the midpoint. I can do that with my ruler and compass, and I make some pieces of a circle on each side, and then I look at the places where this circle meets them, and then if I connect those 2 points, those 2 new marked points, I get a perfect perpendicular bisector of this segment. So the ancients knew how to do a triangle and a hexagon the way I did it. They knew how to do a square, because you can make these perpendicular lines, and that makes it easy to do squares. They knew how to do a pentagon. That's a little more complicated, and that's all they knew. They could put 3 and 5 together to get a 15-gon too. But for instance, you know, what's the next number? We know how to do 3, 4, 5, 6, 7, right? Can you do 7? No one could say. And they asked, can we do this? Is it possible to construct a 7-gon or a 9-gon or anything else at all, other than the ones you can get by taking 3 or 5 or 3 times 5 or dividing those things by 2. You can divide again and again by 2, just the way I did here, to get like a 30-gon or a 60-gon. That's all easy. once you have a 15 gun. It was an open problem from antiquity. For 2,000 years, people played with the ruler and compass and worried about that. And then something amazing happened. It got connected with the rest of mathematics. That often happens in mathematics. When a problem gets connected to something else, it becomes accessible. Actually, this felt a prodigy. A pimply 19-year-old, Carl Friedrich Gauss, in 1796. What he did initially was just to prove that you could construct a regular 17 gun with ruler and compass. And later on, he analyzed the problem completely and said exactly what you can construct. I'm going to do the construction for you that Gauss proved was possible. But if I really do it with ruler and compass, then you'll be very disappointed because it won't work. And that's just because the little errors that I make along the way. There are so many little constructions to make. They're all the same, and they're all really easy. But by the time you're finished, the errors have all built up, and so I might construct a 15 gun instead of a 17 gun. There's my circle. So I would like to construct a regular 17 gun in that circle. So here goes. The first thing I'm going to do is to draw a diameter. So the next step will be to construct a perpendicular bisector of this diameter. Maybe I'll do one such construction just so I'm not cheating completely. I know where one point is already, the center, so I don't have to draw that. Here's the other. And I guess I want it to go on for a while. Okay, you know I can divide things in half with ruler and compass, so I'm going to divide them in half, and I'm just going to do it by eyeball. We could do it with ruler and compass, but it gets tedious after a while. And then I want to divide each of these segments in half too. There's a half, and maybe that's a half, like that. And then I get to draw another line. I'm going to do that with the real ruler through the quarter mark. And then I'm going to do something surprising. I'm going to draw a circle which has this radius. This is half the length of the radius. This radius, and based at that point on this intersection, this quarter mark. So I'll put a little more ink in there, get it in the hole, and I'll draw this semicircle. Now I'm going to draw a couple more lines. This construction has a lot of lines in it, but it's really quite easy.
Do you enjoy this?
I love it. I love it. I don't know why, but it's like origami or something. It's very, very precise craft stuff, and it does something beautiful. I'm going to draw that line. I'm going to draw this line, and I'm going to divide them both in quarters too. So you know I can do that, and I'm going to do it by eyeball again. Well, you know I could. So I want that quarter, and I want this quarter, and I want this one. Is that about half? And this one. All right, and now I'm going to draw some more lines through this point of intersection and through those two new points, and I'm interested in where they meet this line down here. So there's a fundamental point that's going to be useful to me, and here's another. There. Okay, so now I have these two important points on this line marked. And I'm going to do something funny. I'm going to bisect this segment from this point to the edge. It's about here, but maybe I'll do that accurately because this is important. And I'm going to draw a circle whose centered at that midpoint and whose radius is this. So it'll be inside the circle like that. I'm interested in this point, by the way, where my circle meets this line. And I'm going to draw a tiny little circle around the center point with radius this little distance here. So now I have another circle, and what I want is the line that joins them. There. And now I'm going to draw a circle which is centered at this funny point and this radius. So one more circle, and we're almost done. We're almost there.
Are you still enjoying this?
I'm getting a little tired of it, to tell you the truth. I'm going to draw that circle. And the crucial thing is where it meets this line. There. Okay, now we are ready. You might say, well, where's the 17 gone? And I have to draw out a perpendicular to this diameter, which meets at that point and another one here. So I'm going to draw a line here and a line here. And should I eyeball it or should I do it for real? If I'd had a little more energy at this point, I would use the compass, but what I'm interested in anyway is this point and the corresponding point here. Now you might, if you're looking really hard, you might say, that's not a 17th of the circle. And in fact, it's 2/17 of the circle, or it would be if I had done everything exactly right. So I have one more division to do. I draw this line, I divide it in half, and I get a point about here, right? I would say that's the point. And now I have my 17th of the circle, finally, by drawing this radius. One radius and two radius. So this distance from here to here is supposed to be a 17th of the circle. Now, just for fun, and you may have to go off camera for this, Brady, let's see how close I came.
All right.
Now, I would say I didn't get quite halfway between because I estimated that 2, 3, 9, 10, there's another, and another,
Oh dear.
and another. Well, gee, it seems it's close to a multiple. And the last one.
What did you make? What gon have you made?
Let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21. So I made a 21 gon by accident, an impossibility. So it went wrong because it's, I think, probably not even a numerically stable procedure. Even if I'd tried to use the compass at every time and done it as accurately as I could, by the time I made all those divisions and things, little errors would have built up and it would have come out wrong one way or another. But it's provably the right thing if you were exactly right. Let's see, how am I doing? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Here's 16. And then since it's a 17 gon, maybe it should connect this way. Not quite a regular 17 gon, but what can you do? Before I explain that, though, let me tell you the way a mathematician would think about this construction. Here's a circle. And now if I want to construct a 17 gon, what I really want to do is to find 1/17 of the circle. Let's say it's here. I don't know where it really is. What does it mean to construct that? Well, if I construct that point, then I could drop a perpendicular to the line. So I've really constructed this distance. And if you think about it, if this angle is a 17th of 360 degrees, so this angle is 360 degrees over 17, mathematicians usually write that as 2 pi over 17 radians. And so I'm really constructing a number which is the cosine of 2 pi over 17. Or if you like, I'm constructing a number which is the sine of 2 pi over 17. Or if I think in complex numbers, and I think that this is the imaginary axis, here's I, then I'm constructing a number which is cosine of 2 pi over 17 plus I times the sine of 2 pi over 17, and that's e to the 2 pi I over 17. That's a variant of Euler's formula. Euler, the one everybody knows, is that if I took half a circle, so 2 pi over 2, which is, this is the angle 2 pi over 2, which of course is just pi, then Euler's formula says that if you take e to the pi I, that's equal to -1. And there's -1 on the real axis. So that's the usual way to write Euler's formula, but actually it works for any angle. And so I'm trying to construct one of these numbers. They're all equivalent. And so Gauss was interested in what numbers you could construct with ruler and compass. What possible numbers? And he proved a truly amazing theorem, or we think he proved it. I really do think he proved it, but he didn't write down a full proof. That was left for another 40 years. He didn't bother again. He believed in proving just a few really important things. He said, "Pauca sed matura" was his motto, few but ripe. Anyway, he exactly showed which numbers you could construct with ruler and compass. And it turns out that the ones you can construct are the ones you could write in terms of square roots of things. So what Gauss actually did was to find a way of solving an equation like z to the 17 minus 1 equals 0. And when I say solving, I mean writing down the roots in terms of simpler things, in this case in terms of square roots. And that's what you need to be constructible. So he showed, this is going to be a big formula, that the cosine of 2 pi over 17 was equal to minus 1/16 plus 1/16 times the square root of 17 plus 1/16 times the square root of 34 minus, inside the square root sign, 2 times the square root of 17. You're allowed to take iterated square roots in this, plus 1/8 times a big square root of 17 plus 3 times the square root of 17 minus the square root of 34 minus 2 times the square root of 17, and then minus another 2 times the square root of 34 plus 2 times the square root of 17.
Do you know what, Professor? I think it would have been easier for him to get the compass and ruler out.
Yeah, well, this thing comes from an iterative formula that he worked out. He worked out a general method of solving certain kinds of equations in terms of simpler things like square roots. And that's the method that led to the whole big breakthrough. So this is a byproduct of his method, and this construction that we saw, which is so beautiful and complicated, is a byproduct of this byproduct. It was a sort of secondary thing for him, but he was proud of it. And he put it in the very end of his most famous book, Disquisitiones Arithmeticae, as the sort of crowning chapter.
What has he done that showed the 17 com was drawable?
So if you can write the cosine of 2 pi over 17 in terms of square roots and adding and subtracting and multiplying and dividing, that's exactly what you need to know to show that this segment, the cosine of 2 pi over 17, can be constructed with ruler and compass. Once you've constructed that, you make a perpendicular line and you look where it hits the circle, and then you've got your 1/17 of a circle, and you just measure it out, and it goes around 17 times if you did it exactly right. So that's what Gauss knew would work, and what does work, at least in principle, if not with a real ruler and compass.
Was the 17 gone his aim? Was that his end game? Or was that like a byproduct?
I think it was a byproduct of his study of the roots of the equation z to the n minus 1. So Gauss made a very deep study of these equations and what their roots look like in the complex numbers. He used this to prove something much, much more than just the 17 gone. So there are things called Fermat primes, Fermat numbers. A Fermat number, f sub k, is 2 to the 2 to the k plus 1. Now you've got to make it odd, so it has to have a plus 1 to have a chance of being prime. And if you do this, so what's f0? f0, 2 to the 0 is 1, 2 to the 1 is 2, so 2 plus 1 is 3. That's a prime. f1, what's that? That's 2 to the 2 to the 1 plus 1. 2 to the 1 is 2, 2 to the 2 is 4, 4 plus 1 is 5, so that's 5. Another prime. Fermat noticed this, by the way. That's why they're called Fermat numbers. What's f2? 2 to the 2 to the 2 plus 1. That, well, 2 to the 2 is 4. 2 to the 4th is 16. for 16 plus 1 is 17. We've seen those guys before. 3, 5 were what the ancients knew. 17 is what Gauss did. F3, I could go through this whole rigmarole again, but let me just cut to the chase. It's 257. And that's a prime. And F4 is 65,537. And that's another prime. And Fermat said, look, I've found a formula for primes. Now, at the time of Fermat, nobody had the technique to figure out whether F5 was prime or not. And so Fermat just guessed that the series would continue. And it took Euler first to show that F5 is not prime. And in fact, if you look at F5 and you go on computing, as long as we can compute with computers, we've gotten to F32, none of these are prime. So Fermat was just
Well, that's like the
misled.
worst. That's the worst prime generating formula ever.
That's right. It's terrible. It generates exactly 5 prime numbers. What Gauss really proved, I believe, though he didn't write down the proof, it was left to one cell 40 years later, was that the regular n-gons that you can construct, the n for which you can construct a regular n-gon, are exactly the Fermat primes themselves, or products of distinct Fermat primes, or any of those numbers times the power of 2, because you can divide sides in half and as long as you like. So for instance, you could, in principle, construct a regular 65,537 gon, and in a trunk in Göttingen, there is a construction with ruler and compass of that n-gon done by an amateur sometime between Gauss's time and ours. But I'm not sure that anyone has ever checked it to see whether it was right. But you can construct in principle things like 257 times 17 times 64 gon. But that's the only kinds of things you can construct. So Gauss really settled that question by using his technique for solving equations, z to the n minus 1. In the back of his book, this famous book, Disquisitiones Arithmeticae, you can see my copy has taken some beating. Gauss is proud, and he's so proud that he wrote down all the n-gons that you could construct in the first 300 numbers. All the numbers under 300, that is. So you can see they're scattered around, and there are a lot of them. There are infinitely many. So if you give me n, I have to write n as a product of primes, powers. So I write n as a power of 2 times a power of some other prime. K might be 0, so the 2 might not be there. P1 to the A1 times P2 to the A2, etc., where the pi are prime.
Any prime.
Any primes. And then I look, and I say, if any AI is bigger than 1, then not possible. That's point 1. If any of the pi are not equal to F0, F1, F2, or F3, then not possible.
These are the Fermat.
Those are the Fermat primes.
But only the first 3.
That's all the Fermat primes we know. Well, maybe there's another Fermat prime, but any Fermat prime could go in that list. People don't believe there are any more Fermat primes,
What about
actually.
F4?
Did I leave out F4? Oh, F4, yes.
F4, yeah.
Or F4,
Yeah.
or other Fermat primes. Then it wouldn't be possible. So you don't have to have all the Fermat primes, but you can't have any other primes in the factorization. So I guess the surprising thing is that there's a connection between how you factor a number into primes and whether you can write down a ruler and compass construction of a regular n-gon.
So Fermat thought he'd come up with a great prime generating formula.
Yes, right.
He hadn't, but he'd indirectly come up with one of the components of constructing.
That's right. That's right. You can, if you have 2 to the n plus 1 for other numbers, you can show that n has to, and if it's prime, then n has to be a power of 2. So those are the only primes that you could write this kind of way.